All right, so now we have all of the mechanics that we need for this to make sense. Let's talk about section 9.10 and discuss Taylor series. We have seen that an infinite series can converge to a finite amount. We have seen that some series involving variables called power series can converge to a particular function. In particular, we've seen things that were either geometric or related to a geometric series. But what about functions in general? Well, let's start off with the definition. This is section 9.10. So our definition is related to the Taylor polynomial that we saw earlier in the chapter. Let f of x be a function with all order of derivative defined at x equal to c. When we say all order of derivative, we mean first derivative, second derivative, third derivative, fourth derivative, forever. Every derivative is defined at c. Now, it may be defined as 0, but that's okay as long as it's defined. So let f be a function with all order of derivative defined at some number c. Then the sum as n goes from 0 to infinity of the nth derivative of f at c over n factorial times x minus c to the power n, which is the same as saying f of c plus f prime of c times x minus c, plus f double prime of c over 2 factorial times x minus c squared plus ... plus the nth derivative of f at c over n factorial times x minus c to the power n plus ... That is called the Taylor series for f at c. If you notice, it's the Taylor polynomial without an end. If you went from n goes from 0 up to some number, that would have been the Taylor polynomial. The first degree, second degree, third degree, fifth degree, 20th degree polynomial approximation of a function. But with a Taylor series, we're taking the Taylor polynomial and expanding that out so that it has no end, so that we continue on forever. Notice that this is a power series. After all, that's a constant, plus a constant times the first power of x, a constant times the second power, constant times the third power, constant times the nth power, on forever. By definition, this is a power series, but it's the power series whose terms come from the Taylor polynomial. Incidentally, if we had a Taylor polynomial centered at 0, we call that a Maclaurin polynomial. Likewise, if you have a Taylor series centered at 0, that's called the Maclaurin series. And here, my handwriting has seen better days. Maclaurin series, like that. So that means we can create a function. We can start with a function and create a Taylor series from that function. Okay, so for example, let's say I'm going to take this function f of x is equal to sine of x. I can create a Taylor series. So let's write the Taylor series. And here we're going to center it at 0 with c equal to 0. Or in other words, the Maclaurin series. All right, well, we just need to find our coefficients. Here we're centering things at 0, so that's going to be f of 0. And then we're going to want f prime of 0. And then f double prime of 0, f triple prime of 0, the fourth derivative at 0, the fifth derivative at 0, and so forth and so on. All right, well, let's see what those are. F at 0, that's sine of 0, which is just 0. F prime of 0 will be cosine at 0, which is 1. The derivative of sine is cosine, and I'm going to go and plug in 0. The second derivative would be the derivative of the cosine of x, which is negative the sine of x. But again, I'm going to plug in 0, which is still 0. And then I have negative the cosine of 0, which is negative 1. If I take the derivative of negative cosine of x, I get the sine of x again. Oh, but I'm plugging in 0, so that's going to be sine of 0, which is 0. And then if I take the derivative of the sine of x, I get the cosine of x. But then I'm going to plug in 0 since that's my center. And here I notice I have a pattern, 0, 1, 0, negative 1, 0, 1, 0, probably the next one will be negative 1, and so forth. Okay, so our Taylor series looks like this. We're going to get, let's go ahead and write it right here. That's going to be 0 plus 1 times x. Here we would say x minus c, but since c is 0, we don't have to bother. Right? We can write x minus 0, but it's not really a big deal. Plus, let's see. The next one's also 0 over 2 factorial. Right now I'm going to write all the zeros. In a minute I'll make sure they all drop off. So that'll be 0 over 2 factorial times x squared plus, and then now my next coefficient is negative 1 over 3 factorial x to the power 3. And then my next coefficient is 0 over 4 factorial x to the power 4. And then the next one would be positive 1 over 5 factorial x to the power 5, and so forth and so on. Remember, this is a series. This is an infinite series, so it goes on forever. Here I notice that a bunch of these terms are zeros, so let me not even bother writing them. Here I can rewrite this as just 1x plus, well, that should be a negative, so plus negative 1 over 3 factorial x to the third, plus the next one will be positive 1 over 5 factorial x to the fifth. Here, just so that I can establish a pattern, let me write this as 1 over 1 factorial. Hey, look, positive, negative, positive. I think the next one will be negative, right? In fact, you could even confirm that. Continue taking derivatives, and sure enough, the next one that's not 0 is negative 1. And that would be over, well, let's see, 1 factorial, 3 factorial, 5 factorial. The next one in the pattern would be 7 factorial, like this. And then the next one would be positive, negative, positive, negative. The next one should be positive 1 over 9 factorial x to the 9 plus dot, dot, dot. Well, at this point, I realize that I have a very nice pattern here. So here I can write this using the summation notation. I can write this as the sum as n goes from 0 to infinity. Right? N goes from 0 to infinity of. Well, okay, my numerator is an alternating pattern. Plus 1, minus 1, plus 1, minus 1. We know how that works. That's going to be minus 1 to the power of n. Right? Because if you have n is equal to 0, negative 1 to the 0 is 1. But then to the first is negative 1. And then to the second is positive. And to the third is negative. And then positive, and so forth and so on. So that alternating pattern is just given by the sum as n goes from 0 to infinity of minus 1 to the n. Well, now what about my denominators? Well, my denominators are factorials. Oh, but they're not every factorial. They're every other factorial. They're the factorial of every odd power. Or sorry, of every odd number. Oh, well, we saw how to write odd numbers in section, what would that have been? I guess that would have been section 9.1 when we were talking about writing the nth term of a sequence. All right. So here, that's going to be, to write an odd number, we write this as 2n plus 1 factorial. Because, of course, here, if I take 0, well, that's 0 plus 1. Oh, that's 1 factorial. If I say n is equal to 1, 2 times 1 is 2, plus 1 is 3. Oh, yeah, the next one is 3 factorial. And then if I say n is equal to 2, well, 2 times 2 is 4, plus 1 is 5 factorial. Oh, yeah, that does give me all the subsequent odd numbers. And then I have x to the power, and I notice these powers are the same as the coefficients without the factorial. So here I'll write this as 2n plus 1. And there we go. This is our Taylor series for that's generated by the sine of x. Okay? So we can take this function and we can form a Taylor series. Now, of course, a Taylor series is only as good as when it converges, just like any other series. So now a follow-up question was, okay, now what is the interval of convergence of this thing? All right, well, the interval of convergence of this thing, well, let's go ahead and use a ratio test and find out. So let's go ahead and perform the ratio test, which wants us to take the limit as n approaches infinity of the absolute value of the n plus first term over the absolute value of the nth term like this, which is going to give us the limit as n approaches infinity of, well, let's see, here are our terms. We're going to go ahead and take the n plus first term. So make this n plus 1, n plus 1, and n plus 1. So that's going to be minus 1 to the n plus 1 over 2 times n plus 1 plus 1 factorial times x to the power 2 times n plus 1 plus 1. And since it's times, that's part of the numerator. And now I'm going to divide by the nth term, which is the same as multiplying by the reciprocal of the nth term. So here I'll take the 2n plus 1 factorial and put it on the top. And I'll take my x to the power 2 n times 1 plus 1 and put that on the bottom. Okay. Oh, and I suppose I have a minus 1 to the power of n down here as well. Okay. So here all I've done is I've taken my nth term, and anywhere there was an n, I've put an n plus 1, n plus 1, n plus 1. And over here, I've taken my original nth term and said I'm going to divide by it, so let me multiply by its reciprocal. I flipped it. Oh, I guess this should just be 2n plus 1. That one should not be the one for the n plus first term. That should just be the one for the nth term. So that should just be over negative 1 to the n, and then over here it's just x to the 2n plus 1. Like that. There we go. Okay, now notice I'm taking an absolute value of things. So because I'm taking an absolute value, these are irrelevant. It doesn't matter. All these do is change things from positive to negative. But since I'm taking absolute values, that's not going to affect anything ever. So here that's just because of the absolute values. Because of absolute values, these, and that includes this one, are just 1. All right, because here this would either be negative 1 or positive 1. Same thing here. But if they're either negative 1 or positive 1, and I'm taking the absolute values of everything, well, they're always just positive 1. So here I get a much nicer expression with fewer things in it. Limit as n approaches infinity of the absolute value of. Here, let me just write this as 2n plus 2 plus 1 more. Okay, so 2n plus 3. And same thing here, that's 2n plus 2 plus 1 more. That's 2n plus 3 factorial. Times 2n plus 1 factorial over x to the power 2n plus 1. And here you notice a bunch of stuff's about to cancel. And if you don't notice that, well, let's write it out. Limit as n approaches infinity of, here, x to the power 2n plus 3. I can write that as x to the power 2 times x to the power 2n plus 1. Because if I add those powers, I get that power. But now notice the reason I've done that is so now it'll cancel that with that down here. These two are about to disappear. I can do the same thing over here. 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 and below, which is 2n plus 1 factorial. But now I have a 2n plus 1 factorial in the numerator, which means I now have two very large terms divide out. And over here we have two very large terms divide out. So now I can write this limit as n approaches infinity of something much simpler. This is x to the power 2 over 2n. Here, let me multiply this out. That'll be 4n squared plus 4n plus 6n. That will give me plus 10n plus 6. Notice that as n approaches infinity, this is not changing. Only this is changing. So this is something that's staying fixed over something that's going to infinity. That's equal to 0 for all x. So the Taylor series converges for all x. Okay, cool. Before we move on and see anything else about this, notice what we've done. We took a function. we used it to generate a Taylor series and then said, oh, and by the way, that Taylor series converges for all real numbers. Before we continue, go ahead and try the following example. Go ahead and find the, let's take the function f of x to equal e to the x. Go ahead and write the Maclaurin series, again, centered at 0. Write the Maclaurin series generated by f. And find its interval of convergence. Remember, there's only 3 possibilities. It either converges only at its center, since it's a Maclaurin series, that would be 0. It converges for all real numbers, or it converges in some interval from -1 to 1 or from -5 to 5 or something like that. So go ahead and give that a try. Pause the video and generate the Maclaurin series using f and find the interval of convergence. When you're done with both of those tasks, unpause the video and we'll go through it together. All right, so let's take a look here. First of all, let's generate the Maclaurin series. We're going to take our f of x and we're going to plug in 0. And then what we're going to do is we're going to take the subsequent derivatives of those and plug in 0 all the way. Just like that. Now this one's actually really rather nice because, of course, the derivative of e to the x is always e to the x. So here f of 0 is e to the 0, which is 1. But then every subsequent derivative is exactly the same. So here, f prime is also e to the x, so you can plug in 0 and that's 1. And then f double prime is e to the x, and f triple prime and f quadruple prime. Every derivative is e to the x, so every time we plug in 0, we're going to get e to the 0, which is 1. All right, so now we can go ahead and write this out using our definition. We know that the Maclaurin series, or the Taylor series centered at 0, is simply going to take the derivatives. It's going to divide them by a factorial and then multiply by x minus the center raised to the same power as the factorial you took. All right. So this will be, well, our numerators are always 1, which is nice. So that's going to be 1 over 0 factorial, x to the 0, plus 1 over 1 factorial, x to the 1, plus 1 over 2 factorial, x to the 2, plus 1 over 3 factorial, x to the 3. They're always 1 in the numerator. My denominators starting from 0 are factorials, and my my powers are always the same as the denominator without the factorial. Plus ... Okay, so this one's not too bad because I can really quickly see the pattern here. This goes from n equals 0 up to infinity. The numerator is always 1. The denominator is just n factorial, right? If I start at 0, with 0 factorial, then 1 factorial, 2 factorial. Okay, so that's n factorial. And my x is always being raised to a power that's the same as that denominator without the factorial. Or in other words, x is being raised to the nth power. So here we can write this as 1 times x to the nth power, which is just x to the nth power. All right, so there we go. There's a Maclaurin series. This one's a little bit nicer than the previous one because the other one required us to worry about a little extra messiness. We had odd powers and odd numbers in our denominator. But, well, you'll notice that it's still, even in this case, not too bad. The other part of the problem was to find the interval of convergence. And again, because we have a factorial here, and in fact, whenever we generate a Maclaurin or a Taylor series, we're always going to have factorials. The ratio test is generally going to be our go-to way of testing. In previous sections, we saw series that were generated by a geometric series. Okay, well then we can use a geometric series test. But for Taylor and Maclaurin series, since factorials are a natural part of their definition, then that means that the ratio test is generally going to be the way we want to test for their convergence. So let's give that a try. We're going to take the ratio test. And that's going to be the limit as n approaches infinity of the absolute value of the n plus first term over the nth term, which for our case is going to be x to the power n plus 1 over n plus 1 factorial, divided by, which is the same as multiplying by the reciprocal, x to the power n over n factorial. So I flipped it around to divide by it. Okay. So all I'm doing is I'm taking the nth term, I'm looking at the next one up, which would change this n to an n plus 1, same thing there, and then I'm dividing by this nth term. And if I'm dividing by a fraction, that's the same as multiplying by the reciprocal. That's flipped around. So now things simplify significantly. So here, limit as n approaches infinity of the absolute value of those. Okay. So now this will simplify significantly. This is the limit as n approaches infinity of x times x to the power n. Right, after all, if you add those powers, that'll give you power n plus 1, over n plus 1 factorial is n plus 1 times n factorial, times n factorial over x to the power n. And now you notice that the two biggest complications are about to go away. N factorial divides n factorial, and x to the n divides x to the n. So this gives us the limit as n approaches infinity of the absolute value of x over n plus 1, like this. So notice now that as n approaches infinity, this is some value that's not changing, but this is approaching infinity, right? Here, n is what's changing, which means x is just x, right? You chose a value for x, well, that's the value of x. But whatever you chose, that's what it is. However, n approaches infinity. So here, this is something that's not approaching infinity over something that is approaching infinity, and that's going to go to 0. And this is for all x. Okay? So because this goes to 0 for all x, that means that, well, the limit of our ratio test gave us something that's less than 1 for all x. So the series converges for all x. Okay? So that's our interval of convergence from negative infinity to infinity. And that makes us happy. Now that brings us to the most important part of this. We have seen that given a function, we can generate a power series. Okay, we have seen that that power series converges. In this case, it converges for all real numbers. In another case, it might converge just on the interval from -5 to 5. Whatever. That series converges for some interval, maybe the entire number line or maybe some subset thereof. But what does it converge to? We know that given a function, we generate a Taylor series, and we see that that Taylor series converges for at least some values of x, in this case for all values of x. But if it converges, what does it converge to? Well, this brings us back to Taylor's theorem. So recall, and this was Taylor's theorem from a previous section, 9.7, I believe. Taylor's theorem says that the function f of x is approximately equal to its Taylor polynomial. Well, we can make it exactly equal to its Taylor polynomial. We can make it equal to n goes from 0 to infinity of, let's see, let's write it as a Taylor polynomial. So that's going to be f, nth derivative of f evaluated at the center over n factorial times x minus c to the power n plus some remainder. That was Taylor's theorem. Here I'm glossing over a few things, but essentially it said that the function is equal to its Taylor polynomial plus this little extra, where the remainder of n, or the nth remainder, is going to be given by f n plus first derivative evaluated at z over n factorial of x. Oh, right. Okay. So here, this is generically for any c. So x minus c to the power n plus 1. And here, that should be n plus 1 factorial. Just like that. So where x and c are on either side of z. So I guess I should say where z is between x and c. Okay. All right, so Taylor's theorem tells us that our function is approximately equal to its Taylor polynomial. Okay, well then shouldn't it be approximately equal to its Taylor series? After all, its Taylor polynomial is just the, that shouldn't go out to infinity. This should only go up to some capital N. There we go. So here we're talking about Taylor's theorem, which is a finite number of terms. So this is the finite series. The first 5 terms, 10 terms, 50 terms. But these terms of our finite series are the first 5, 10, 50, or 1,000 terms of our Taylor series. So if this one is good enough to be approximately equal to f, shouldn't the Taylor series also be approximately equal to this? Well, sure. It's going to approximately equal to that. Oh, but what do we make about this remainder? Well, if this is having more and more terms, that means that this will have a bigger and bigger denominator. This will have a bigger and bigger power. So what's happening is, as we have more terms here, all of these are growing to infinity. This n, or I guess I should say this n plus 1, are growing to infinity. So what will happen to that remainder as n approaches infinity? Well, depending on what happens, we get the following. And this is a theorem. Let's begin with a Taylor series. Let S be given by the sum as n goes from 0 to infinity of f, the nth derivative of f evaluated at c over n factorial times x minus c to the power n. So let's let S be the Taylor series that's generated by f. Centered at c. If r sub n, meaning this remainder term, if this approaches 0, so if the limit as n approaches infinity of r sub n is equal to 0 for all values of x in an interval I, then S is exactly equal to f of x for all x in I. Or in other words, as long as this remainder term goes to 0 as n approaches infinity, and here let me write that a little bit bigger, that should be n approaches infinity. As long as this remainder term goes to 0, that means that your function that generates this Taylor series is also equal to the Taylor series. Or in other words, if I use e to the x to generate this power series, then e to the x is equal to this power series, so long as this remainder goes to 0. The proof of that is very, very short, so let's just go through that. Let's begin with the Taylor series. And let's say we have the nth partial sum given by the Taylor polynomial of degree n. So let's see. Consider the sum as n goes from 0 to infinity of f nth derivative evaluated at c over n factorial x minus c to the power n. Okay, so that's a Taylor series. The partial sums sum as n goes from 0 to just some value n of the nth derivative of f at c over n factorial x minus c to the power n, and that's a nth degree Taylor polynomial. So if you just let that go to infinity, that's a Taylor series. But if you stop before you get to infinity, if you stop with 5 terms or 10 terms or 100 terms, that's your Taylor polynomial. Here, let me call this one S. And here, let me call this one the same thing we called it in the previous sections. We'll call it P sub n, where you have the nth Taylor polynomial. Okay? Or the nth degree Taylor polynomial. All right, well, here, notice that the partial sum of this Taylor series is the nth Taylor polynomial. So here we get that S sub n is equal to P sub n. The nth partial sum is equal to the Taylor polynomial. The nth partial sum is the polynomial, that one. So here the nth partial sum is equal to the nth Taylor polynomial. Okay, but we also know that the function f of x is equal to the Taylor polynomial plus some remainder. Okay, well then that means that if I subtract this over this way, the Taylor polynomial Pn is going to equal to f of x minus that remainder. Well, yeah, but if S sub n, if the nth partial sum of our Taylor series is equal to the nth Taylor polynomial, and the nth Taylor polynomial is equal to the function minus that remainder, here, by plugging this in for P of n, I get that the nth partial sum of my series is given by f of x minus r of n. But we know that the nth partial sum converges to the series as long as you let n approach infinity. But if these are always equal to each other, then I should be able to take the limit of both sides. The limit as n approaches infinity of the nth partial sum is equal to the limit as n approaches infinity of the function that generated that sum minus the remainder, the Taylor remainder term. Oh, well now this is just S, right? The limit of the partial sums is my series. Here, the limit as n approaches infinity of f of x is just going to be f of x. After all, f of x is not dependent on n. F of x is just its own separate function. Minus the limit as n approaches infinity of our remainder term. So that means that if this is 0, the series is exactly equal to the function. So if the limit as n approaches infinity of the remainder term from Taylor's theorem is equal to 0, then S is equal to f of x, meaning that the function that generates the Taylor series is equal to the Taylor series it generates. I'll say that again. If your remainder term goes to 0, that means that the function that generates the series is equal to the series that it generated. And that concludes our proof. Okay. As an example of that, let's go back to an example we saw a moment ago. And that was we generated a Taylor series out of the sine function. We said sine of x is given by this Taylor series. And the interval of convergence of the Taylor series turned out to be from negative infinity to infinity. So we know this converges to something. Does it converge to the sine of x, though? Well, it depends on what happens to the remainder term of the Taylor expansion, of the Taylor polynomial. So let's go ahead and do that. Going back to this problem, let's see, example, what happens to the remainder term of Taylor's theorem for f of x equals the sine of x as n approaches infinity. Okay, so let's see here. We know what the remainder term looks like. We know that's going to equal to the n plus first derivative evaluated at some number z. Now, we don't know what z is, but we know it's somewhere between our center. In this case, we found our center at 0, and c, some number that we're plugging in. So we're going to take take its n plus first derivative at z over n plus 1 factorial times x minus, I suppose we don't need x minus anything because we're centered at 0. But here, let me go ahead and write it in the most generic form. Okay, so like that. So here we take the remainder term is given by f, the n plus first derivative of f. We're going to evaluate it at z over n plus 1 factorial. Okay, now remember, whenever we took derivatives of the function f, we either got sine or cosine. And sine or cosine, whatever number we plug in, will always be between minus 1 and 1. So here, recall, any derivative of f of x is either sine or cosine, or negative sine or negative cosine. Okay. Now here we don't know what number we're plugging in, but we know we're plugging it into sine of x, cosine of x, negative sine of x, or negative cosine of x, which means that, so for any z, we know that f of n plus, f of n plus 1, the n plus first derivative of f at z must be between minus 1 and 1. Because sine and cosine of x are between minus 1 and 1. So it doesn't matter what we plug in there. So that means that our series has our polynomial has a remainder term whose numerator is bound between minus 1 and 1. Okay, so that means that our r sub n is bound between, well, if that's my numerator, that's going to be 1 over n plus 1 factorial times x minus c to the power n plus 1. And over here, that's going to be negative 1 over n plus 1 factorial times x minus c to the n plus 1. All I'm doing is I'm saying, well, this is going to remain the same, but the biggest this will ever get is 1. So my remainder might be as big as that. And the smallest this ever gets is negative 1. So it could be as small as that, or somewhere in between. Oh, but both of these I can take a limit of, right? Here I'm going to go ahead and note that my center is at 0, since c is equal to 0. Here, even if our center was somewhere else, it turns out to be the same result. But here, let's go ahead and do this. Since our center is at 0, we get r sub n is less than or equal to, here I'm just going to write this as x to the power n plus 1 over n plus 1 factorial, and is going to be greater than or equal to negative x to the power n plus 1 over n plus 1 factorial. Oh, but what we want to do is we want to find out what happens as n approaches infinity. Okay, so then Let's take the limit of everything. Let's take the limit as n approaches infinity of minus x to the power n plus 1 over n plus 1 factorial, which is less than or equal to r sub n, which is less than or equal to that should be the limit as n approaches infinity of r sub n, which is less than or equal to the limit as n approaches infinity of positive x to the power n plus 1 over n plus 1 factorial, like that. But if we go back to section 9.1, we saw that whenever you take a limit of a sequence, whenever you have an exponential in the numerator and a factorial in the denominator, this will grow significantly faster than this one. So here, this will go to 0, and this will go to 0. So by the squeeze theorem, if the left side goes to 0 and the right side goes to 0, then the thing squeezed in between has no choice but to go to 0. So here the limit as n approaches infinity of r sub n is going to go to 0. Oh, but then by our theorem, we see that as long as that limit goes to 0, then we get that for all x in the interval of convergence, our Taylor series converges to the function that generated it. So, because the limit as n approaches infinity of the nth remainder term is equal to 0, then the sine of x is in fact equal to, it doesn't just generate this Taylor series, it's equal to this Taylor series, is equal to the sum as n goes from 0 to infinity of minus 1 to the power n over 2n plus 1 factorial times, what was that? X to the power 2n plus 1 in the interval of convergence. Which is from minus infinity to infinity. Or in other words, this is a somewhat strong statement. This function is exactly equal to this series no matter what number you plug in. This is something of use computationally. If you open up a calculator, I don't mean physically, but I mean the programming of a calculator. Calculators can't do a lot of the things that their buttons say they can do. A calculator cannot take the sign of a function. You might think it can because there's a sign button, but that's not how that works. All calculators know how to do is add. Right? But notice, that's all this is. This is a sum, which means if I wanted to take the sine of x, and let's say I didn't know how to do that. Let's say I didn't even know what sine of x was. It doesn't matter because this sine of x can be written exactly as this. So this is equal to, what was that? X to the power 1 over 1 plus x to the power, that should be minus x to the power 3 over 3 plus x to the power 5 over 5, and these are all factorials, minus x to the power 7 over 7 factorial plus ... So if all you knew how to do was add and subtract, you could still find the sine of x as to any level of precision you wanted. Because after all, you have an infinite number of terms. So here you add up the first 5 terms, or the first 3 terms. Okay, well then that's the answer I wanted. Oh no, that's not good enough. Okay, add up the first 20 terms. Is that as good as you wanted? No? Okay, keep going. Add up as many terms as you want until eventually you get one that fills up your screen. Until eventually you get one that has this level of precision that's as high as you need it to be. In a bit of a, what's the word? I guess unexpected would be right. In a bit of an unexpected turn, it turns out that the sine of x is a polynomial. Okay, it happens to be an infinitely long polynomial, but it is a polynomial. After all, that's what that theorem says. It says that that as long as this goes to 0, which it did, these two are equal to each other. But this is just an infinitely long polynomial with an infinite number of terms. So I'm going to abuse the notation here a bit, because when we say polynomial, we mean a polynomial of a certain degree. Usually polynomials end. So here I'm abusing my language a little bit, but in essence, the sine of x is a polynomial. It just happens to be a really long polynomial. It turns out that a lot of our other functions are polynomials as well. Or rather, it turns out that a lot of other functions are going to converge to their Taylor series. Here, I'm not going to go through the derivation. You can if you like for extra practice. But we saw the exponential function e to the x. And we generated a power series for that one as well. We generated a Taylor series. It turns out that if we go through this procedure of trying to find out the last term here, it turns out that we can actually do the same thing. We can confirm that the exponential function e to the x is in fact equal to its own Taylor series for all real numbers. So here, let's go ahead and state some known Taylor series. The first three that we see, the first three that we're going to look at, we've already seen two of them. The sum as n goes from 0 to infinity of the sine of x. Oh, what am I doing? I'm starting with the function. There we go. The sine of x is equal to the sum as n goes from 0 to infinity of minus 1 to the power n over 2n plus 1 factorial times x to the power 2n plus 1. Just like that. We also have e to the x. E to the x is equal to its power series. And again, I'm not going to go through the confirmation. I believe there's actually one in your homework that asks you to confirm it for e to the x anyway. But here I'm going to go ahead and state the result. E to the x is in fact equal to its own power series. The r will end up going to 0. And here that's going to equal to x to the power n over n factorial. This is true for all values of x. And so is this one. Cosine of x. We could go through and build the Taylor series of the cosine of x. And maybe we should. But here, let's be a little bit lazy about it. In a previous section, we saw that as long as you have a function that converges to a Taylor series, or I said that backwards, as long as you have a series that converges to a function, then I can take the derivative of one by taking the derivative of another. Yeah, but I know the derivative of the sine function, that's the cosine function. And since this converges to the sine of x for all real numbers, then we suspect that its derivative will also converge to the cosine of x for all real numbers. In fact, that is the case. Here, we shouldn't just assume that. We should go through and confirm that. But again, here, let's see what our result is. We know how to confirm it, and in your homework, you'll have some exercises that have you confirm these anyway. So basically, I'm leaving the annoying work to you guys. Yeah? So here we could say, all right, I'm going to take the derivative with respect to x. Okay, well, let's just take this, bring it down, subtract 1 from the power. I'm going to go ahead and do this on a different page here. If I take the sine of x is equal to the sum as n goes from 0 to infinity of minus 1 to the power n over 2n plus 1 factorial, that's equal to x to the power 2n plus 1, just like that. Okay, but now if I want to take the derivative of one side, that's the same as taking the derivative of the other side. Okay, but now I can write that as the sum of the derivatives of the individual terms. Because as long as these converge, which they do, then I have the ability to treat this like I would normally treat a polynomial. And that is to say I'm going to take its derivative one term at a time. Now you might be concerned with, how do I take a derivative of something that involves a factorial? You don't have to. This is a constant. Remember, the derivative is with respect to x. These are just numbers. That makes it easy. Take that number, bring it down, subtract 1 from the power. So here that's the sum as n goes from 0 to infinity. This all stays exactly the way it was. But now, take this number, bring it to the front, 2n plus 1, and then subtract 1 from the power. Well, make that plus 1 go away, so that just leaves me 2n, just like that. Notice that this is 2n plus 1 factorial is really 2n plus 1 times 2n factorial. I can write this as n goes from 0 to infinity of minus 1 to the n over 2n plus 1 times 2n factorial. We've had lots of practice with that so far. Times 2n plus 1 times x to the power 2n. But now these divide out, gone and gone, and we're left with the sum as n goes from 0 to infinity of minus 1 to the power of n over 2n factorial times x to the power 2n. And this is our Taylor series for the derivative of the sine of x. Or in other words, it's the Taylor series for the cosine of x. So that's the sum as n goes from 0 to infinity of, and I already forgot what I got, that's going to be negative 1 to the power of n over 2n factorial x to the power 2n. And this will also converge for all real numbers. And here I've taken a bit of a shortcut to give us what the series would look like. Here in reality we should go through and check its interval of convergence, and we should check to see that r is going to 0 as n approaches infinity. But it does turn out that both of those things are true for this series. And so here we have our Taylor series of some well-known functions: sine of x, cosine of x, and e to the x. This generates this and is equal to this. This is equal to the series that it generates. Note that in a previous section, we saw that once you have a function defined with a power series, you can treat it the way you normally treat a function, which means you can make substitutions. This brings us to a extremely powerful integration technique. Consider the following problem. We're going to integrate e to the minus x squared. This is not doable by the fundamental theorem of calculus, meaning I cannot take an antiderivative of this and then plug in the endpoints, right? And here I can say, okay, let's plug in the endpoints. That's not going to happen. You say, why not? Because this is not the derivative of any elementary function, meaning there are no polynomials, rational, radical, trigonometric, logarithmic, exponential, hyperbolic, or really any other function you've ever heard of whose derivative is this. Which means that finding an antiderivative is not possible. It turns out that this is actually a lot easier to handle than you might think, and it doesn't require anything that you would recognize as integration, and yet it works quite well. So here, let's start off by saying, let's note that e to the power of x is equal to the sum, as n goes from 0 to infinity, of x to the power of n over n factorial. All right, that's our power series for e to the x. But I don't want e to the x. I want e to the minus x squared. Okay, well, that's a function. Do what you always do with functions. Plug it in. So here I'm going to take, if I have f of x is equal to e to the x, I don't want e to the x. I want e to the negative x squared. Okay, well then just plug that in. So that's going to be the sum as n goes from 0 to infinity of, let's see here. That's, instead of having an x right there, I'm going to have a minus x squared right there. Just like that. Here I can rewrite this. That's the sum as n goes from 0 to infinity. Here that's minus 1 times x squared. So let me distribute my power here. That's minus 1 to the n times x squared to the n, which is x to the 2n. All right, negative 1 to the n. x squared to the n, I will take those powers and multiply them together, which will give me x to the 2n over n factorial. Okay, so that's the power series of e to the minus x squared. And since this one converges for all real numbers, that means, well, this is defined for all real numbers, so that means the power series also converges for all real numbers. Here, this is exactly equal to that. So if I want to take the integral of that, well, why not take the integral of this? So the integral of e to the minus x squared dx is the same as the integral of the sum as n goes from 0 to infinity of minus 1 to the n, x to the 2n over n factorial. But now, as long as these converge, as long as this series converges, I can switch these two limits. And we know this converges for all real numbers. So here we can write this as the sum as n goes from 0 to infinity of the integral of minus 1 to the n over n factorial times x to the power 2n. Oh, but now, with respect to x. Oh, but now I can integrate. Here, I don't have to worry about this one. This is just a constant with respect to x, right? Here, I'm integrating with respect to x. That's the variable. These are just numbers. So here, that's going to be the sum as n goes from 0 to infinity of, let's see here, that's minus 1 to the power n over n factorial. Here, that's just a monomial term. I'm going to add 1 to the power and then divide by the new power plus some constant of integration. And that's it. You might say, well, what is that? That's the answer. Well, yeah, but what function is that? Is that e to the something? Is that logarithm of something? It's actually not any known function. There is a name for this. Once people figured out that this could be done, there were names given to certain functions. This one's called the error function for reasons that I'm actually not sure about. They're not exactly in my area of study or expertise. But here, it doesn't matter what this converges to. We know that it converges, and that is the integral of our function. So there we go. This might not be something that you immediately recognize as an integral. It doesn't look like anything we've seen before. And yet, hey, if these are equal, then the integral of this should be the same as the integral of that. So if I take the integral of this one, which I can do since those are just monomial terms, well, then the integral of this must be that. And that gives us our result. This gives you an alternate technique for dealing with integration. Now, one thing to be warned about here, if you're using this to find this result, we don't actually know what it converges to, as I've said probably 2 or 3 times already, which means that if you are trying to get some nice number here, if you're trying to say, oh, I'm going to integrate from 1 up to 5, that we don't know what it converges to. We know it converges, which means if you're patient, you can sit there and plug in numbers over and over and over again and eventually get a good approximation. But here, we know it converges. We don't know what it converges to, and so using this for a definite integral would still have some complications. But for an indefinite integral, where we're just trying to find an antiderivative, that is a perfectly acceptable answer. And of course, it's the only answer that's possible, since this doesn't have an antiderivative in any other recognizable form. So, for example, here, if I was trying to find the integral from 0 to 1, just for example, here, well, that's my antiderivative. So now I could evaluate from 0 up to 1. Obviously, if I plug in 0, all of these terms will be 0. 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. Okay, because anything to the 0 to any power is equal to 0. So plugging in that 0 makes all of that 0. So here, if I plug in the number 1, that's going to give me 1 to the power 2n plus 1 over 2n plus 1. Right? So here, let's actually write that out. So let's say what we wanted to do was we wanted to find the integral from 0 up to 1 of e to the minus x squared dx. Well, that's going to be, and here I'm going to go ahead and skip the derivation because it was exactly the same one we just saw. I'm just grabbing that answer. And that's a sum as n goes from 0 to infinity of minus 1 to the power n over n factorial x to the 2n plus 1 over 2n plus 1. Here I'm going to leave off the plus c because this is a definite integral. Okay, so that's going to equal to the sum as n goes from 0 to infinity of minus 1 to the n over n factorial. Here we're plugging in the number 1 to the power 2n plus 1 over 2n plus 1 minus the sum as n goes from 0 to infinity. Right? We plugged in the number 1, and now we're going to plug in the number 0 and subtract. So it's minus 1 to the power n over n factorial, 0 to the power 2n plus 1 over 2n plus 1. I took that, plugged in 1. I took that, plugged in 0, and subtracted. Okay, but now all of these terms are 0. 0 plus 0 plus 0 plus 0 on forever. Oh, so this will always be 0. That's gone. Here, that's not 0, but that's always the number 1 right there. So here, this reduces down to the sum as n goes from 0 to infinity of minus 1 to the n over n factorial. Here, that's just the number 1, so let me not even bother writing it, although I could write right here the number 1. But my other denominator is still there, which is 2n plus 1, like that. So here, this would be that integral from 0 to 1. Obviously, we don't know what that converges to, but if you needed an estimate, you can now start taking terms. Notice this is an alternating series. Okay, so what? Well, that means I could write out the first few terms. This is negative 1 to the 0 is 1 over 0 factorial times 2 times 0 is 2. 2 times 0 is 0 plus 1 is 1. The next one would be negative 1. This would be 1 factorial. 2 times 1 is 2 plus 1 is 3. The next one would be positive 1 over 2 factorial. And 2 times 2 is 4 plus 1 is 5. And then the next one will be minus 1 over 3 factorial times 7. And then 1 over 4 factorial times 9, and so forth and so on. But remember, with an alternating series, if you add up the first 4 terms, then this 5th term estimates your error. So here, let's say, okay, I want to know what this integral is. Well, it's that infinite series, and I don't know what that converges to. Oh, that's fine. Let me just take an estimate. Let me add the first few terms together. So that's going to be what? 1. So 0 factorial is 1. So that's 1 over 1, which is 1. And then that's 1 factorial is 1 times 3 is 3. So minus a third. Plus, let's see, 2 factorial is 2 times 5 is 10. That's 1/10. Minus 3 factorial is 6 times 7 is 42. Plus 4 factorial is what? 24 times 9. That's 216. Right, so 1 over 216. Okay, so here, plus dot, dot, dot. Here, if you wanted to find an estimate, you would say, okay, let's add up the first few terms. If I add these together, I get, let's see here. Okay, let's grab one of these things. All right, let's see. 1 minus 1/3 plus 1/10 minus 1 over 42. 42. And that's equal to 26 over 35. Right, so 26 35ths. All right, but of course, we don't have an actual answer. That's only an estimate. But remember, going back to section 9.5, we saw that the alternating series, if you just take the very next term, the absolute value of the next term gives you the amount of error that this one has. So here, my actual answer is this plus or minus 1 over 216. Or in other words, my answer is going to be somewhere in between. The integral from 0 to 1 of e to the minus x squared dx is bound somewhere between. Well, if I take 26 over 35 and I add 1 over 216. That's going to give me, that's an interesting number, isn't it? 5,651 over 7,560. And if I take 26 over 35 and I subtract 1 over 216, I'm going to get 5,581 over 7,560. So I don't know exactly what this integral is, but I know it's somewhere in between those two numbers. If that's good enough accuracy for you, if you're okay to be within that much of your answer, awesome. If whatever application you need requires you to have a greater level of precision, well, then just keep going until you get the level of precision you like. So even for a definite integral, this is not exactly the right answer. It can't get you the right answer unless you know what this converges to. But, unless you know what this converges to. But you can get an estimate that's as good as anything you'll ever need. And finally, the last thing, in fact, one of my favorite things in this course, let's go ahead and use this to, here, let me change some lights here. And no, I'm not being dramatic by setting a mood with mood lighting. It's just getting dark where I am. All right, so here we go. We saw 3 Taylor series. And we saw that for these Taylor series, our functions converge to their Taylor series for all real numbers. And the series were as follows. The sum as n goes from 0 to infinity of x to the power n over n factorial. All right? This is equal to e to the x for any value of x you could ever hope for. We saw that the sine of x is equal to the sum as n goes from 0 to infinity of x to the power 2x plus 1. That's going to be negative 1 to the power n over n factorial. All right, so there's our Taylor series for the sine function. And that should be 2n plus 1 factorial. And finally, we saw that the cosine function, cosine of x, is equal to the sum as n goes from 0 to infinity of minus 1 to the power n, x to the power 2, that should be an n, x to the power 2n over 2n factorial. Okay. Before we continue anything else, just a little bit in terms of language. You'll remember way back when in trigonometry, you see the sine function and you see the cosine function. And they tell you, oh, by the way, cosine is an even function because if you plug in x or if you plug in minus x, you get the same thing. And you wonder, okay, I guess that makes sense because of the way sine and cosine are defined on the unit circle. But, you know, the name just sounds weird. Why is that even called an even function? Hey, check it out. All of our powers are even. The reason this works like x squared does, where it's symmetric on the left side and on the right side, is because it is an even-powered set of terms. The sine function is an odd function because all of its terms have odd powers. So this makes the names make a lot more sense. Even functions are even functions because their Taylor series are made up of just even terms, even-powered terms. Odd functions are odd because their Taylor series are made up of just odd-powered terms. So that's not what I was getting at here, but that's just something that I thought about right now because I wrote these out together. This is even. Well, yeah, all the powers are even. This is an odd function. Well, sure, all the powers are odd. What did you expect them to be, right? Okay, but that's not what I was getting at here. Let me write out these in their longer forms, meaning instead of with a summation notation, let me write them out just a few terms. Okay, well, this one is x to the power 0 is 1 over 0 factorial. So that's going to be 1 over 0 factorial, which is just the number 1. All right, so let's just write it that way, the number 1. And then I don't have any alternating terms here. There's no plus or minus. So here these are all plus. So it's going to be plus x to the power 1 over 1 factorial. And that one's x to the power 2 over 2 factorial, x to the power 3 over 3 factorial, x to the power 4 over 4 factorial, and x to the power 5 over 5 factorial. Okay, and of course that does keep on going. But here that's good enough for what I'm about to do. I can write out the terms of sine of x. Again, I start with n is equal to 0. Well, that would be positive. This would be a power 1, and this would be a 1 factorial. Okay, so it's going to be a positive x to the 1 over 1 factorial. When n is equal to 1, well, this is now a negative, so that's minus. Here I can write this as x to the power 2 plus 1. Okay, so that's going to have a power 3 over 3 factorial. And then if I say n is equal to 2, well, that's going to be negative 1 to the 2, so that's a positive again. And that's 2 times 2 is 4, plus 1 more is 5. So that's x to the power 5 over 5 factorial. All right? The power is the same as the denominator, but the denominator has a factorial. Plus dot, dot, dot. It just keeps on going that way. Cosine of x, I can do something similar. When n is equal to 0, this is negative 1 to the 0, which is 1. X to the 0, oh, well, that's just 1. And then over here I have 2 times 0, which is 1 factorial, which is, 2 times 0, which is 0 factorial, which is 1. So here if I put a 0 here, that's a 1. That's a 1. And 0 factorial is also a 1. So if I put all those together, that's just the number 1. If I say n is equal to 1, well, that's negative 1 to the first power. That's going to make that a negative. 2 times 1 is 2. Okay, so I'll have x to the power 2. And then that's the same number as that, but with a factorial. And then I have, well, let's see. That's if n is equal to 2. Well, now negative 1 to the 2, that's positive again. 2 times 2 is 4. So it'll be x to the power 4 over 4 factorial. And then like that on down the line, dot, dot, dot. Notice something. 1, 1. X squared over 2 factorial. X squared over 2 factorial. X to the 4th over 4 factorial. X to the 4th over 4 factorial. Here, this has every other factor of this. That one, and that one. And you're saying, oh yeah, but that's only every other one. What happened to the ones in the middle? Well, that's these. Hey, look. This one is the first term, the third term, the fifth term. This one is the second term, the third term, the second term, the fourth term, and the sixth term. So putting these together gives me e to the x. You say, no, it doesn't. Look, the signs are wrong. Okay, yeah, that one matches, but this one has the wrong sign. And yeah, that one matches, but this one has the wrong sign. Okay, so it's just close. It's not exactly the same. It was just a coincidence. Well, no, it turns out we can do just a little bit more than that. Because now, let's bring in one of my very favorite things in the whole wide world. I'm going to take this and I'm going to substitute something in here. You say, oh, so instead of x, you're going to do like x squared or minus x. Yeah, something like that. But what I'm going to do is I'm going to substitute in one of my very favorite things in the world. That's an imaginary number. I'm going to take ix. You say, the imaginary number? What does that have to do with anything? Well, let's see what happens. You might say, well, wait a minute. How do you know that that's going to work? Because I've seen this many, many times before, and because I have experience with these things. And you say, well, how do you expect us to know this works? I don't expect you to know it works. That's what I'm showing you. So here, e to the ix is equal to, the sum is n goes from 0 to infinity, of ix, and I guess I should just write this together, ix to the power n over n factorial. All right. All I'm doing is I'm plugging in, instead of an x, I'm plugging in an ix. Okay, so that's going to be 1 plus ix to the first over 1 factorial plus ix squared over 2 factorial plus ix to the third over 3 factorial. Notice I'm just taking that very first line, and instead of an x, I'm putting an ix. That's how these usually work, yeah? I'm replacing this x with an ix. I'm replacing all of these x's with an ix. And if you want to, you actually can generate this out the long way, but here I'm going to do it by substitution. And that's ix to the 4th over 4 factorial plus ix to the 5th over 5 factorial plus dot, dot, dot. That would keep on going, but that's sufficient for us. And here I wanted to mirror the original one that I made. Okay, well, that's going to equal to 1 plus I times x over 1 factorial. Right? Now, when I take I squared, by definition, that's negative 1. So here we're going to go ahead and recall the definition. I is equal to the square root of negative 1, or an alternate definition, I squared is equal to negative 1. We're going to be using that here in just a moment. I squared is equal to negative 1. X squared is, well, it's x squared over 2 factorial. I to the third. Well, I to the third is I squared times I. And since I squared is negative 1, that really is just negative 1 times I. So that's going to be negative I x to the third over 3 factorial. All right? I to the third equals I squared times I. But since I squared is equal to negative 1, that's negative 1 times I, which is just negative I. Here, I to the fourth. Well, I to the fourth is I squared times I squared, which is negative 1 times negative 1. Oh, that's a positive 1. So that's going to be plus 1 times x to the power 4 over 4 factorial. And then over here, I can do the same thing with a negative, with I to the 5. And that's going to be I to the 4 times I. We just saw I to the fourth is 1. So that's 1 times I, which is just I. I to the fifth is I. X to the fifth is x to the fifth over, and 5 factorial stays the same. But now notice, this is the same as that. This is the same as that, including the sign, the positive. And I say, well, wait a minute, there's an I there. We'll worry about that I in just a moment. Here, this is the same as this, including the sign. That's got a negative on it. This is the same as this. Oh, except for that I on there. This is the same as this, including the sign. This is the same as this. Well, not quite. After all, I have I's on some of them. Well, here, let's write this a slightly different way then. Let's write this as, let's keep all the ones that don't have I's together. We're going to say 1. Okay, so that's every other term. So 1 minus x squared over 2 factorial. And then over here, that's going to be plus x to the fourth over 4 factorial. And then that will keep on going, right? Every other one would not have an I on it. And then let's take all the ones that do have I's on them. So that's going to be I, x over 1 factorial. That's going to be minus I, x to the third over 3 factorial, plus I, x to the 5 over 5 factorial, plus dot, 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 like that on forever. Well, notice this has a common factor of I. So you can factor out an I. Right? So here that's going to be 1 minus x squared over 2 factorial, plus x to the fourth over 4 factorial, plus dot, 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 plus I factored out an I from all of these, x over 1 factorial, minus, I take out the I, but the minus is still there, x to the 3 over 3 factorial, plus, I take out the I, that plus x to the 5 over 5 factorial, plus dot, dot, dot. But notice, this is exactly cosine of x. Now the signs match, right? Positive, negative, positive, and so forth. So this thing right here is exactly the sine of the cosine of x. And notice this thing right here is exactly the sine of x, including all the positives and negatives. All right, that's positive x over 1 factorial, minus x to the third over 3 factorial, plus x to the 5 over 5 factorial. It all matches up. Oh yeah, but that sine of x is being multiplied by I. So this gives us that e to the ix is equal to cosine of x plus I sine of x. This is the very, very beginning of complex analysis. This is the very beginning of calculus with complex numbers. We're not going to go any further into it. This is as far as we get to in Cal 2. And in Cal 3, we sort of revert back to real functions. But if you go past Cal 3 into differential equations and beyond, the analysis of complex numbers becomes very, very important. And this is a result that you'll see used in differential equations and beyond. This is called Euler's formula. Euler's formula is simply stating that e to the x, sine of x, and cosine of x are very, very similar to each other, to the point where if you simply take the sine of x and multiply it times I, combining it with the terms of the cosine of x, that's going to give you e to the x, assuming x had an imaginary coefficient, an imaginary power here. Right? Euler's formula can be thought of a slightly different way. Note that if I have e to the ix, that's equal to cosine of x plus I sine of x, just like that. We can show that, and I'm not going to go through the derivation because it's exactly the same as the one we just saw, except that instead of plugging in an ix, you plug in a negative ix right here for all of these. If you go through that full computation, you get almost exactly the same answer, except here, instead of a plus, there's a minus, cosine of x minus I sine of x. So here we can show, and that's a mathematician way of saying, yeah, it's true, but I don't want to go through it. We can show that e to the minus ix is equal to cosine of x minus I sine of x. Okay, so what? Add those two together. E to the ix plus e to the minus ix, okay, that would equal to cosine of x plus I sine of x, plus this one would be cosine of x minus I sine of x. And now if I combine those, notice I sine of x plus a negative I sine of x is 0. So this gives me e to the ix plus e to the minus ix is equal to cosine of x plus another cosine of x is cosine of x times 2. But now if I divide on both sides by 2, I get that the cosine of x is equal to e to the ix plus e to the minus ix over 2. Remember, in a previous chapter, we saw the cosh function, the hyperbolic cosine function, and I said, oh, it's defined using exponential functions. It looks like this. And I don't know if you remember me saying it or not, but I said we'll come back later and we'll talk about how it relates to the cosine function. We'll talk about why it's defined this way and why this definition has us calling it a hyperbolic cosine. What does this have to do with cosine? It has to do with the fact that the hyperbolic function is the same as the regular cosine function with, here, this allows imaginary values, whereas this one involves only real values. Basically, the entire time you've ever seen the cosine function, you've only seen what happens with real values. What you haven't seen is what happens when you have imaginary values. It turns out that sine and cosine are not bounded between -1 and 1. Cosine and sine can go on forever. You can have cosine of a number that gives you a much bigger number, but you wouldn't have a real value. For example, here, let's say I take the cosine of, let's just keep it simple. Let's say 2i. Let's take the cosine of 2i. Okay, well then that's going to equal to e to the I times 2i plus e to the negative I times 2i over 2, which is equal to, let's see, I times I is -1, and -1 times 2 is -2. So that's e to the -2 plus negative I times I, I times I is -1, but that extra negative makes it a +1. +1 times that 2 gives me a power of 2, all over 2. And now let's see what that is. If I take e to the power 2, if I take e to the power 2, and add to that e to the power -2, and then divide by 2, I get 3.762195691 ... And there we go. I just took the cosine of a number and got something bigger than 1. It's not that sine and cosine are only bound between -1 and 1. That's actually not true. Cosine and sine have an infinite range. You can plug in numbers and get whatever you want out of cosine. Same thing for sine. The difference is that, or not the difference, the statement should be, if you're restricted to real numbers, sine and cosine are bound between -1 and 1. If you're allowing complex numbers, sine and cosine can be anything. Right? Here we get e to the ix equals cosine of x plus I sine of x. This is Euler's formula. And this is the start of complex analysis, the start of using complex numbers in calculus. Here, this isn't anything particularly important here, the fact that I can now compute the cosine of 2i. This is just a single example of what can come out of this. This is the important thing once you start going into differential equations and beyond. Incidentally, you could do the same thing for the sine function. Let's see here. We can do something similar for the sine function. Instead of having these two and adding them together like we just did, we could always subtract them. And we could have e to the ix minus e to the minus ix. Well, that's going to be this one, cosine of x plus I sine of x, minus this one, which is cosine of x minus I sine of x, like that. But now by subtracting those, these two subtract away, and we're left with e to the ix minus e to the minus ix is equal to, well, here double negative makes that a plus, so that's going to be a positive 2i sine of x. And so I can divide both sides by 2i, and this gives me that the sine of x is actually a complex variable, function given by e to the ix minus e to the minus ix all over 2i. Right? So here, these are alternate representations of the cosine and the sine function. And they do shed a little bit of light as to why we defined this thing as the hyperbolic cosine. Oh, because it is the cosine function, restricting ourselves to only real numbers. Same thing over here. We said that, recall, that the hyperbolic sine function, sinh of x, was given by e to the x minus e to the minus x over 2, which again you'll see is very close to the alternate representation of the sine function. All right. So here, this concludes our chapter. This shows us how we can use Taylor series to, first of all, represent functions. Second of all, how to take those functions represented by a Taylor series and be able to integrate in a way that was not possible before. We could integrate things that don't have a traditional antiderivative. And we see the very first inklings of higher level mathematics, in this case complex analysis, which allows us to compute things in the complex plane, compute things with traditional functions thought of in new ways, and it allows us to see some of the limitations that we had before start to disappear on us. Right? So that is it for our section and for our chapter. As an assignment for this section, go ahead and try section 9.10. Don't worry, this won't appear on it. Section 9.10, try problems, go ahead and try 5 through, let's say 19, 5 through 19 odd. And then let's try 27 through 39 odd. And 43, 63, and 67. And that should suffice. If anybody has any questions, please make a note of them, reach out to me and let me know. And I hope you all have a good day.